Since the dawn of real-time communication, we have been trained to wait. The moment you press the call button, you wait for someone on the other side to pick up their phone while it is ringing. This wait is designed to be part of the system. You expect it because this is how human conversations start. However, when you're talking to an AI, this expectation is gone. You expect the AI to be instantly available and ready to answer your questions. The funny thing is, there's a lot of things happening behind the scenes before the AI can start answering. The client and server need to establish a connection before they can start exchanging media. It only takes a few seconds, but this silence feels awkward. This is what we define as the awkward pause. The moment when nothing seems to happen. You don't know if the AI is thinking or even worse, not listening. So we decided to eliminate this pause entirely. We redesigned how RTC systems work for conversational AI use cases and challenged fundamental assumptions. The result was a conversation that feels much smoother, faster, and natural. And in this small shift, we redefined what real time truly means for AI conversations. I am Ishan, Software Engineering Manager on the AI Calling Infra team at Meta. Along with my colleague Hani, a software engineer on the RTC platform team, we are going to share our talk on Ultra Low Latency Connection or ULLC for conversational AI use cases. So before diving into optimizations, let's first understand why latency matters. In human conversations, timing is everything. It's the constant back and forth that makes a conversation feel fluid. If there is an unnecessary pause, it breaks the rhythm of the conversation. So when you are talking to an AI and you want the AI to feel like they are a human companion, latency becomes critical. Then we have use cases where instant feedback is not just good to have, it's essential. Think about conversation starters, which are pills on the app that are personalized to a user that they can tap to ask questions. In this case, users don't have the patience to wait for too long for the AI to reply. And if the AI takes too long, that moment of curiosity can be lost forever. Then there are also use cases where people are on the go. They are driving, multitasking. They have questions like, where is the nearest gas station? Or what is the next meeting on my calendar? These questions need immediate answers. And this brings us to the broader truth. As a species, we have become less patient. We live in a world where apps load instantly and you can send messages in real time to users across the country. The AI systems need to keep pace with this technology. That is why we chose to optimize connection latency as a critical metric and came up with an innovative design for ultra low latency or ULLC. So before diving into optimizations, let's first understand what are all the things that we did before we designed ULLC. We tried to eliminate every unnecessary delay from the system and pick up as much low-hanging fruit as possible. The first optimization that we came up with is for audio buffering. Normally, RTC systems would start recording audio after the client and server connections is established. However, we realized that we could start recording immediately after the user presses the call button. All of that audio would be safely stored in a local buffer and could be sent after the connection is established. This made the experience so that users could start talking immediately on pressing the button, and it felt much smoother. The next optimization was bursting all of this audio quickly after the connection is established. It's a natural extension to the buffering optimization, where we realize that we don't need to play this in real time just like a human would talk. Instead, the LLM can listen at a much faster rate and make sense of it. The next optimization was in how the WebRTC negotiation process works. In WebRTC, the client sends its local STP and negotiates technical details such as codecs, transport protocols, and encryption parameters. Since we have a static server, we could just send a hard-coded local STP immediately on user button tap with a bunch of fixed parameters. This would parallelize a lot of the latency with other WebRTC initialization and save off precious milliseconds from the connect flow. Finally, we made a lot of optimizations on the server side, like starting the LLM in parallel with establishing the RTC connection. This meant that as soon as the server receives user audio, it was ready to process it and send out a response. All of these optimizations made the experience feel much more real time and smooth. However, even with all of this, we were not able to break the 1 second barrier for connection latency. This is when we realized that we needed to change something fundamentally and address the major bottleneck that was staring at us. And that was the connection bottleneck in how the connection itself is established. So, in the rest of the talk, we will go over the ULLC design and how we tackled this major bottleneck. Next, we will talk about results that we see by using ULLC in a production environment. And finally, we will see what opportunities lie ahead and how this design can be applied to use cases even beyond AI. So to go over the ULLC design, I will now hand it off to my colleague, Hani.
Thanks, Ishan, for going over the use cases and for the detailed overview of how we got to this point. To fully appreciate the ULLC breakthrough, we kind of need to understand the old way of doing things first. In the traditional real-time communication architecture, the connection establishment is inherently sequential. The design requires at least 2 round trips between the client and the server, which is the primary source of the initial delay. This diagram demonstrates the 2 round trip approach used in the traditional way of doing things these days in RTC applications. The flow starts with the signaling round trip indicated in the white lines in the diagram, where the client sends the session creation request to a central signaling service, which in turn initializes and coordinates 2 internal services. In here we have the bot service, which is responsible for AI logic and LLM. In addition, we have the dedicated media service, which handles audio streams and routing for them. Once the resources is allocated, this signaling service will package important connection details and the IP address for the media service and send it back to the client, something called the join response. Once the client receives this response, it will start the media round trip. In the media round trip, the client starts sending stun pings and then RTP packets to the media service, which is at this point we have the connection established. This negotiation approach, though functional and adaptable, it introduces delays. The time the client is waiting for the first round trip is considered dead time. This delay is really the connection bottleneck our team is determined to eliminate. So in ULLC, the main concept in the design is really to run both the signaling request and the media path at the same time in parallel. By initiating these tasks in parallel, we really eliminated the first round trip, saving a lot of time. This diagram shows how we perform things in parallel in ULLC, reducing this critical delay by 1 RTT. The media path here involves the client first doing a DNS lookup on a specific meta media edge entry point where it gets an IP. This IP is then used as an ICE candidate to start sending the stun request to it. At the same time, the client also initiates the signaling path with sending a session creation request to the server. On the server side, the request handler will receive this request and starts a new session, the bot service session here, and store important connection information or session information in big cache. The stun will use this session information in big cache to find the bot service and route the media to it, causing the session to be established, a connection to be established. Really here, co-location of these services is crucial. The magic truly happens if both the initial request and stun routed to the same data center. The core challenge in ULLC lies in the consistent routing of two distinct yet interdependent streams to the same data center. If the stun packet went to a completely different DC where the session is not being set up, the connection will fail immediately. To reduce the chances of this happening, we introduced edge to DC latency mapping, which we can use to find the closest DC to a specific edge. This is an example of how this mapping would look like. Basically, it contains entries for each edge and DC and their RTT times between them. The RTT latency timings frequently updated, and the whole map gets deployed to the places where it needs to be. I mentioned earlier that the client will perform a DNS lookup on the media edge entry point. This would resolve to the closest edge to the client. We also expect the client to include this IP and send it to the server in the session request. This is a crucial point for this co-location to happen correctly. The session handler will use this IP to find the closest DC to create the session into it. On the other side, the media edge will use the same map to find the DC to forward the packet to. If both components use the same configuration and the same map, then the routing will happen correctly and they will land in the same DC. However, in some rare edge cases, this map could be outdated or different between these two places due to deployment issues, leading to a mismatch. So in the very worst case where the signaling and media went to completely different DC, the stun is going to fail and the connection will fail. To make ULLC work in this case, we implemented the fallback path. In the fallback path, the request handler will respond back with the updated and corrected connection information, including the updated IP. Then the client will use this information to re-establish the connection and recover it, and then everything will work. However, while this results in normal latencies, because here we're doing 2 round trips, it at least ensures full reliability in these cases. Given the constraints of ULLC, we cannot really wait on the remote STP coming from the server, similar to how the standard RTC way doing it. So in ULLC, the client is responsible more of setting up the connection. The client will generate both ITIs and server secrets along with other connection information and package it and send it to the server on a secure channel. At the same time, the client will use this information to create both local and remote STPs and pass it to WebRTC for the media path to start. In the case of fallback, the client will use the new information provided by the server to recover and reestablish the connection. As we have discussed, media edge domain lookup is a crucial part of designing ULLC. To optimize this even further, we do the lookup before the call. We even cache the IP to disk to improve further call scenarios. This IP address is then used as an ICE candidate for the connection. While this DNS lookup is used for discovery, it does come with it operational challenges. For example, in cases of edge draining, the DNS will have a population latency of roughly 15 minutes, where the client within that time will have an invalid IP. Luckily, using fallback path, we can recover the connection in these cases. Now that we understand how the ULLC work and all the architecture behind it, let's give it to Ishan to show us how these fundamental changes translate into real-world performance.
Thanks so much, Hani, for that wonderful overview of a really intricate design. Now that we know how ULLC works, let's see what are some results that we see from applying it in a production setting. With ULLC, we were finally able to break that 1 second connection latency barrier. And as you can see in this video, the experience now feels much snappier than before. Not only that, we were able to successfully connect a lot more calls than before. These are users who would otherwise get frustrated and shift to using other apps. More than just connected calls, we also see increased engagement for high intent use cases like conversation starters. These are pills that users can tap to ask questions, and in these cases, users just want quick answers to really simple questions. Moreover, we were seeing a huge drop off from users that were experiencing high latencies, even upwards of 2 or 3 seconds. We were able to prevent this and increase the total number of users that use AI products from Meta. So now let's think about what are the opportunities that lie ahead and how ULLC design can be used in applications beyond just AI. There are a lot of opportunities that we are really excited about. The first one is edge inferencing. Currently, the entire ULLC design revolves around AI systems that are deployed in data centers or DCs. However, Meta AI is a global product and we have users in all corners of the world. Edge inferencing means being able to deploy AI systems in small distributed clusters that are close to the users, called edge. This minimizes the time that data has to travel and helps in reducing latency. However, this comes with challenges of its own. The edge and DC can have multiple round trips and lead to increased latency. So we will need to carefully think routing, caching, and how data flows in this distributed system to bring the benefits of ULLC design. The next opportunity that we are really excited about is audio capture. Now that we have eliminated the connection bottleneck, the bottleneck actually shifts to how the audio is captured. Even though we can start capturing immediately on user button tap, it still takes time to initialize the audio device and start recording from the microphone. We are thinking about ideas where we could parallelize initializing the audio device or even use wake words such as "Hey Meta" so that the recording is already active and the user query can be sent to the server immediately. This could bring even more latency wins on top of ULLC. The next area is media processing. So far in the ULLC design, there is nothing that is specific to AI. There are many other scenarios like editing video with the help of AI, live translations, or creative tools powered by AI. These traditionally have been built on top of HTTP streaming. However, that is not built for real-time performance. We could apply the same ULLC design and we could see much smoother previews and much faster connect latencies for these scenarios as well. Finally, let's talk about wearables, a space that has been expanding rapidly. In the recent MetaConnect conference, Mark announced a new line of Ray-Ban Meta AI glasses. These are for people on the go. And for devices like these, ultra low latency becomes critical. However, these devices come with their own challenges. The latency is distributed across multiple network links between the glasses and the phone and the server. So it needs a lot of careful thinking on how ULLC design can be adapted for these use cases. So, in summary, with ULLC, we have pushed the boundaries of what is possible and how AI systems can be made truly real time. However, this is just the beginning, and we are excited for the roadmap and potential opportunities that it unlocks. I am incredibly grateful to the AI calling and RTC teams at Meta who have helped us every step along the way to land this design. We thoroughly enjoyed working on this challenge. And if you are just like us and excited about making AI systems more performant, please feel free to reach out to us. I'm sure that you will be able to use these techniques to build performant AI applications and bring the benefits of AI to everyone across the world. Thank you so much for your time.